Hey everyone, and welcome to The Explainer. Today we're zeroing in on a material that is quite literally holding modern defense and advanced technology together. We're talking about tungsten. Now, this isn't just a story about a heavy piece of metal, it's an incredible high-stakes journey, one that starts with dirty, complex rocks in the ground and ends with the ultra-pure, critical chemical intermediates that make everything from hypersonic penetrators to the microchips in your smartphone actually work. We're going to trace that fascinating path from the mine all the way down to the molecular level and really dig into the massive global pressure cooker that this supply chain is currently sitting in.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the global tungsten crunch, then look at Wolframite versus Scheelite, followed by the grade diminishing returns, the APT processing bottleneck, the 4 APT grades, and finally, we'll wrap up with the O'Callaghan's Mine challenge.
Section 1. The global tungsten crunch.
So to really grasp the science of tungsten, you first have to understand the massive structural problem with its global supply. Right now, China controls about 80% of global tungsten production. On the flip side, the US has had absolutely zero domestic commercial production of this critical mineral since 2015. We're relying entirely on these heavily concentrated international supply chains for a metal the West simply cannot do without. And that reliance? Well, it's led to this staggering number right here. We saw a 900% price surge for Rotterdam APT, which is the benchmark intermediate tungsten product, between mid-2024 and April 26. This is not just some normal market fluctuation. It's a massive structural repricing. It honestly signals a sheer panic rippling through the global supply chain, with buyers realizing they might not be able to get their hands on this material at literally any price.
And why the panic? Well, it's because of this geopolitical ticking clock. Back in May 2024, the U.S. Department of Defense expanded its supply chain prohibitions. Then, by early and late 2025, China responded. They tightened export controls and strictly limited export licenses to just a handful of state-approved firms. And sitting right at the end of this timeline is January 1, 2027. That's a binding U.S. regulation that legally forces the defense supply chain to stop acquiring tungsten mined, refined, or melted in covered nations, like China. So the West Defense Industrial Base is legally forced to find alternative sources by 2027, which has sparked this massive scramble to build new mines and refineries completely from scratch.
Section 2. Wolframite versus Scheelite. Now, what's really interesting about this slide is the physical reality of how we extract this metal. Knowing we urgently need new sources, we basically have two very different primary ores to look at commercially. And the contrast in how we have to treat these two rocks is just staggering. Scheelite is, well, it's relatively cooperative. It's a calcium tungstate that's amenable to flotation. That means we can use chemicals to make it float to the surface for collection, and it's easily dissolved later on. Wolframite, on the other hand, is an iron manganese tungstate, and it is a totally different beast. It requires really complex physical handling, gravity, spiral, and centrifugal separation. It can also be pulled out using its paramagnetic properties, meaning it's weakly attracted to magnets. The takeaway here is you can't just treat them the same way. Your entire multi-million-dollar processing plant has to be custom-built for the specific rock you're pulling out of the earth.
In fact, there's a famous quote in mineral processing circles about wolframite: heavy as iron, but fragile as glass. It's incredibly dense, but it's also extremely brittle. If you leave it in a crushing ball mill for even a tiny bit too long, it literally shatters into these microscopic slimes that are under 30 microns in size. And once it's that fine, traditional shaking tables and gravity chutes, they just wash the valuable tungsten right away into the tailings pond. So to capture it, modern plants have to use advanced centrifugal concentrators. They spin the material at an astonishing 300 times the force of normal gravity just to pull those microscopic specks of tungsten out of the waste. It is an absolutely amazing feat of physics.
Section 3. The grade diminishing returns. Now, you might be thinking, well, if we need more tungsten, just mine more ore, right? I wish it were that simple. We are facing a massive geological headwind globally. Just take a look at the drop in average Chinese ore grades. Back in 2004, they were mining ore that was roughly 0.42% tungsten trioxide. Fast forward to 2024, and that average has fallen to 0.28%. That is a 33% deterioration in ore quality over just 2 decades. And this isn't some temporary dip. This is the systematic depletion of the highest quality, easiest to process deposits on Earth. Basically, we're having to move a whole lot more dirt to get the exact same amount of metal. And translating those dropping percentages into real-world consequences is honestly pretty sobering, because processing lower-grade ores demands exponentially more energy just to crush and grind the rock. Your processing costs skyrocket, and your actual recovery of the metal per ton mined completely plummets. Plus, from an environmental standpoint, it means an enormous chemical excess. Just to get 1 ton of our final purified product, which is called APT, the traditional processing of these lower-grade ores can generate over 25 tons of high-salinity acidic wastewater. It is a massive environmental and engineering strain. Section 4, the APT processing bottleneck. So no matter where you mine the ore, it almost certainly has to become this chemical first, ammonium paratungstate, or APT. Over 75% of all global tungsten production must pass through this exact specific chemical state. Think of APT as the flour in a cake. You cannot bake the cake, whether that cake is a defense penetrator, a high-tech semiconductor, or a heavy-duty industrial drill bit, without first creating the flour. Because APT has remarkably low solubility in water, it actually allows chemists to keep the impurity suspended in a liquid solution while the pure APT crystallizes and drops out. It's basically the perfect chemical gateway.
And this brilliantly illustrates the hydrometallurgical gauntlet required to make this stuff. It's phenomenal. Step 1 is leaching. This means brutally digesting the ore in sodium hydroxide or in an autoclave. An autoclave is essentially a giant industrial pressure cooker running at 200 degrees Celsius. Talk about the world's most intense baking recipe, right? Then, step 2 is purification. We meticulously drop the pH to strip out things like silica, molybdenum, and phosphorus. Step 3 utilizes really complex solvent extraction or ion exchange to convert the solution into an ammonium tungstate. And finally, step 4 is crystallization, where we evaporate the liquid to form those precious, pure APT crystals. It's a complete 180-degree transformation from dirty concentrate to a pristine intermediate. What you're looking at here is a solvometallurgical flow sheet, and it really represents the bleeding edge of modern chemistry today. Because of that massive wastewater issue and the crazy high energy requirements of traditional autoclaves we just talked about, researchers are desperately trying to improve these historical processes. They're developing flow sheets exactly like this one to reduce those extreme autoclave pressures, limit the excess reagents, and completely eliminate those massive volumes of high salinity wastewater. It is a full-on race to make tungsten extraction cleaner and a lot more efficient. Section 5, the 4 APT grades. Now, once we've finally navigated all that complex chemistry and produced APT, the end-use application completely dictates how pure this chemical needs to be, because not all APT is created equal. The industrial standard is about 99 to 99.5% pure, which is totally fine for your standard industrial drill bits and carbide tools. But as you move down to high purity, ultra-pure 4N, and ACS reagent grades, the requirements become absolutely staggering. To get to ultra-pure for something like semiconductor manufacturing, you need 99.99% purity. That means trace impurities like molybdenum, arsenic, and iron have to be driven down to single-digit parts per million. It requires incredibly stringent lot-by-lot mass spectrometry verification just to ensure it meets those exacting specs. Section 6, the O'Callaghan's Mine Challenge. So let's pull all of this together: the complex geology, the intense chemistry, the grade depletion, and of course, that geopolitical ticking clock. Let's look at a real-world deposit that the West is heavily hoping to rely on in the future: O'Callaghan's. The crucial point here is its mineralogy. This is a massive future Western tungsten resource, but it contains coexisting Wolframite and Scheelite. Remember how differently those two have to be processed? One needs gravity, the other needs flotation. Processing studies have earmarked methods that will actually have to tackle both types simultaneously. Add to that heavy sulfide minerals like sphalerite and galena that act as interferences, alongside elevated impurities like fluorine, bismuth, and molybdenum, which we know are notoriously difficult to strip out during the APT purification stage. This incredibly complex mixed ore deposit perfectly illustrates why achieving Western supply chain independence is a monumental technical engineering challenge, not just a financial one. Which leaves us with the ultimate question. We know the chemistry, we clearly see the declining grades, and we definitely feel the pressure of that looming 2027 defense procurement ban. We have the capital, and we have complex deposits waiting right there in the ground. But can Western engineering and processing technology actually adapt to extract and purify these complicated, mixed ore deposits fast enough to beat that geopolitical ticking clock? It is a high-stakes race between chemistry and time, and the entire modern supply chain is hanging in the balance. I hope this explainer helped you understand the incredible stakes behind the tungsten industry.